Hello everyone, my name is Moein Sorkhei and I'm going to present our work Full Glow for more realistic image generation. Image synthesis in general and in particular street scene image synthesis is interesting for different tasks such as data augmentation for training of autonomous cars. And one approach to doing so is using graphic engines. But those typically require a lot of hand engineering of features, and sometimes images generated by them are not even natural. Another approach to doing so is using generative models, which ideally should be able to synthesize diverse images that resemble natural images. And they're typically used in an image-to-image translation setup, where a conditioning image is used to guide the synthesis of the target image. And GANs are one of the types of generative models which are extensively used thanks to their ability in synthesizing sharp images. Flow-based models, which are invertible probabilistic models with the interesting property of exact likelihood evaluation, have recently gained more attention, especially after publication of GLOW, which was the first model that was able to generate images competitive against GANs. So for image-to-image translation with flow-based models, there have been some works, including CGLOW, which was the first model that introduced conditioning to different layers of GLOW, and then dual GLOW was proposed, which used two GLOW models operating in source and target domains for medical image modality transfer, and CFlow proposed a similar architecture to dual GLOW, where the conditioning was made in the coupling layer, only one of the layers of the GLOW model. And what has not been discovered in these works was how the performance of the model changes if we provide conditioning in all the layers of the model. So what we did was we also used two GLOW models, one operating in the source domain, the other operating in the target domain, where the target GLOW is fully conditioned on the source GLOW, meaning that all the layers of the target GLOW are made conditional on the source GLOW through the conditioning networks. And the hope is that by doing so, we can learn a better conditional distribution of the target domain and could possibly synthesize better images in the target domain. So overall, the general architecture takes a pair of images, one in the source and one in the target domain, during training and tries to optimize the joint log likelihood of the data. In order to compare the performance of the model against previous models, we consider two versions of CGLOW for a fair comparison, one with deeper conditioning networks and one with deeper GLOW. We also compared the performance of the model against dual GLOW and Pix2Pix, which is a famous GAN-based model for image-to-image translation. And we did the experiments on the Cityscapes dataset, which is a popular dataset with natural street scene images. So in order to quantitatively compare the performance of the models, the trained models, we synthesized images on the validation set 3 times. And then in order to evaluate the quality of the synthesized images, we used the pre-trained PSPNet semantic classifier. And also for the likelihood-based models, which are the flow-based models here, we also considered comparing the bits per dimension. And as we can see, thanks to the better conditioning of the target GLOW, we can achieve a lower conditional bits per dimension compared to the previous flow-based models. And we can also achieve a higher semantic classification performance compared to both previous GLOW-based models and the Pix2Pix GAN-based model counterpart. We can have a look at the visual comparison of the samples synthesized by different models. And we can see that the full GLOW model is able to generate images that are of higher quality compared to the previous flow-based models. The Pix2Pix model, the GAN-based model, is also able to generate images with vibrant colors, but they have some undesirable hallucinations, as we can see here. We can also see that by taking different samples of the flow-based models, we are able to come up with different synthesized images where the colors of the objects, for instance, this car here, the color of the objects, for instance, could be different, which is an interesting property when it comes to data augmentation. We can also use the same trained model to transfer the content, a desired content, to another desired structure, which means a segmentation mask here. And the way we do so is that we pass through the model a pair of images and extract the latent representation. And because the model is invertible, we can use the exact same latent representation along with a new condition to synthesize a new image. So we can, for instance, see that by doing so, we can transfer this desired content to a new structure, which results in a synthesized image that is totally different from what we had as ground truth. For instance, notice a difference in the asphalt and the color of the building. And this is simply another example of the content transfer, where we can synthesize a new image where the colors of the cars and the asphalt is different from that of the ground truth image. And that, again, is interesting for extending such a data set. So overall, we proposed a fully conditional glow-based architecture, which, thanks to better conditioning, can generate images that are more interpretable by the semantic classifier. We also synthesized higher resolution images that you can see in the paper if you're interested. We demonstrated promising the results with content transfer, which could be interesting for data augmentation tasks. And in a nutshell, this work could be seen as a step towards closing the gap between flow-based models and their GAN-based counterparts. Thank you very much.